Hi students, so today we start lecture 69 in our aerospace engineering course, and today I am going to discuss about orthotropic and isotropic materials. So in the previous lecture we introduced the general concept of stress strain and the stress strain relationship. We also looked at anisotropic materials. Today we are going to look at the important special cases because these are the materials which are important. They cover materials such as the composite structures which are widely used as well as the typical metals and so on. I am Dr. Ranjan Ganguly. Now, to recap from our previous lecture, let's again look at the stress state and the strain state. So, if you take any point on the aircraft, you are going to get a stress vector and you are going to get a strain vector. So the stress vector has 6 components. The strain vector also has 6 components. So the stress vector will have 3 normal stresses which are denoted by sigma and 3 shear stresses which are denoted by tau, and the strain vector has 3 normal stresses which are denoted by epsilon and 3 shear strains which are denoted by gamma. Now, if we consider the material to be linearly elastic, that is in the linear region of the stress strain curve, then we can get a matrix relation between the strains and the stresses. So this relation in matrix form would be epsilon is A into sigma, where A is a 6 by 6 matrix. And if we expand this matrix out, we get something like this. And this matrix is symmetric. So I have not written the lower part of the matrix because of that. So A12 is equal to A21. So we can clearly see that from this matrix, which is the case for an isotropic materials, you have 21 independent elastic compliances. So if you count these, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So this is the general case of a material, and we are going to now look at special cases which are there, which are of more practical use. So the important special case which is very much useful for composite materials is that of orthotropic materials. Now these materials have 3 orthogonal planes of symmetry. So what happens with that is that many of the terms which are there in the compliance matrix, they become 0. So all these terms here become 0, these terms here become 0, and some term here also become 0. So if you think about it physically, what you can see is that the relationship between the normal strains and the shear stresses is such that there is a 0 matrix here or a 0 submatrix. So essentially there is no relationship here. Similarly, we can see that between the shear strains and between the normal stresses, there is no relationship here. So these couplings are actually removed because of the orthogonal planes of symmetry, and some more terms beside that are also 0, which are the terms specifically here. So this is the matrix we obtain. Of course, it's symmetric. Therefore, you will now see that there are only 9 independent elastic constants. So if you count them, you have 6 in the diagonal here, and you have 7, 8, 9, that is A12, A13, and A23. So this is a much reduced set from the 21 we discussed before, and this is something which is much more amenable to most of the problems which we deal with in composite structures and composite materials. Now, frequently this matrix is written in a form which is more physical in nature. So what happens is that we write A11 as 1 by Ex, we write A22 as 1 by Ey, and so on. So essentially here Ex, Ey, and Ez are the 3 Young's modulus. And the G's here, Gyz, Gxc, and Gxy, are the 3 shear modulus. And beside that, we have 6 different Poisson ratios. So we have nu yx, nu xy, nu zx, nu xc, and nu zy, nu yz. So what happens is that because of the presence of symmetry in this matrix, we can write 3 equations also. So if you look at it in totality, you have 3 Young's modulus, 3 shear modulus, so that's 6, and you have 6 Poisson ratio here, so you would have 12 constants. But what happens is that you also have 3 equations because of symmetry. So finally, the number of independent elastic constants or compliances remains the same as 9. So these equations we can write from symmetry, that is nu yx by ey is nu xy by ex, nu zy by ez is nu yz by ey, and nu zx by ez is nu xz by ex. So what happens here is that if you have one of the Poisson ratio, you can easily calculate the next one. So in most cases what happens is that only one of this Poisson ratio is given and the second one can easily be calculated. So again, this is the matrix or compliance matrix for orthotropic material relating the strain vector to the stress vector. It's a 6 by 6 matrix with many of the terms being 0. Now, in composite structures, we use a slightly different nomenclature. So what we do is that we say the fiber direction is the one direction or the coordinate that is x1, and the remaining two directions which are orthogonal to this direction, they are x2 and x3. So corresponding to x, y, z, we now have x1, x2, x3. So what we have to do is we replace 1 by, or rather we replace x by 1, y by 2 and z by 3, and if we do that we get this matrix here, which you will see in many composite structures books. So here now we have written epsilon 1 1 instead of epsilon xx, epsilon 2 2 instead of epsilon yy, and so on. So you get the point here. Similarly, all these have been changed here. So where we had ex, we have written e1, where we had ey, we have written e2, and so on. So this matrix looks something like you may have seen before. It's getting closer to the matrix which we often have for isotropic material. So we will see that case is a special case of the orthotropic material. Of course, you will realize that for the case of the composite material, you have many more material properties, and so we need to have some way to find these material properties, typically from experiments. So in a composite material you would have these material properties given here. So there are 9 of them. There are 3 Young's modulus E1, E2, E3. There are 3 shear modulus G23, G13, G12, and there are 3 Poisson ratio nu12, nu13, nu23. Remember, the other Poisson ratios can be calculated from the equations I showed in the previous slide. Now, if you have all these material properties, then of course you can obtain the relationship between stress and strain. So if you have been given stress, you can find strain. If you have been given strain, you can find stress from the matrix relationship we discussed before, which was essentially the generalized Hooke's law. Now remember, the fiber direction is always given by 1, and transfers to this fiber direction are x2 and x3. So there are 9 independent elastic constants. Now let's take a look at some of these constants and the typical values of these material properties for typical composite material. So here I have given the numbers corresponding to the As4 carbon epoxy, the boron epoxy, and the S2 glass epoxy. And here we have given the numbers corresponding to E1, E2, G12, nu12, because these are the numbers which are widely used. So in many cases we deal with plane stress problem, we neglect the third dimension. So that's the case here. Now I'm going to make a lecture later to discuss the concepts of principal stresses and so on, and also the concepts of plane stress and plane strain. So we'll come to that later, but right now you can clearly see some interesting things here. For example, you see that E1 is considerably larger than E2. For example, if you take the case of carbon epoxy, it's 140 versus 10. For the case of boron epoxy, it's 205 versus 21. So these are essentially enormous differentials. So what happens is that the composite material is actually very stiff, or it has a good property in terms of E1 in the direction of the fiber, but not in the transverse direction to the fiber. So that's something to remember. If you want to use the composite material strength, you have to tailor the fiber direction accordingly. That's the thing which is going to give you the stiffness in that direction. And also you see the values for G and the values for the Poisson ratios. Now let us come to the one which we are most familiar with from work in strength of materials and even probably in physics in high school, and that is the isotropic material. So whenever you think of materials such as metals, you often think of isotropic material. So in that case, what happens is that we end up with only two material properties. So here I have written the relationship between the strain vector and the stress vector and the corresponding 6 by 6 matrix. Now here you see that E1, E2, E3 have all become simply E. So this is something which is there, and also all the G's are same here. So you have the E, which is the Young's modulus, you have G, which is the shear modulus, and of course you have nu, which is the Poisson ratio here. So very interestingly, you clearly see that you have only two material properties E and nu, because the third property G can be obtained if you have E and nu. That actually is a property which is related to the other two property. This proof comes from somewhere else, and this is something I'm telling you right now. If you ever study aircraft structure in detail or solid mechanics, you know where this comes from. So this is something which is often used in most structural problems, the isotropic material matrix, compliance matrix. And here, for example, if we are talking of materials such as aluminum, which is very widely used in aerospace structures, then Young's modulus would be 70 GPa, nu would be 0.33, and you would very easily be able to calculate the shear modulus G from E and nu value. Now we can get a lot of information out of this matrix. For example, if we want to figure out how we could actually estimate values of E and G, we can do it from this particular matrix given here. So let us assume that only sigma xx is present and all the other stresses are zero. In which case what happens is that I get very simple equation. So I get epsilon xx is simply 1 by E sigma xx. I get epsilon yy is minus nu by E sigma xx, and I get epsilon zz is minus nu by E sigma xx by E. So you clearly see these equations come here, and of course if you are talking of gamma yz, it's all going to be 0 here. So all the shear strains are simply 0. So now from this equation we can see that if we were to take a body and we are going to apply simply sigma xx to it, or a tensile stress, let us say, then what happens is you are going to get a certain tensile strain, and then you are going to easily be able to calculate the Young's modulus E from this equation. So E would be simply stress divided by strain here. Similarly, once you have calculated the value of E, you can very easily calculate the value of Poisson ratio from this equation here, because you know E, you know sigma xx, that is simply F divided by A. So the force divided by the area of the cross section, and you have measured epsilon yy, then you can calculate Poisson ratio. So the first two equations are enough for you to estimate Young's modulus and Poisson ratio for an isotropic material, and of course you can calculate G very easily from the formula I showed in the previous slide. But if you are somebody who likes to do experiment, you can also calculate G by doing an experiment and only doing a shear stress here. That's something you can check out and see. So let us summarize today's lecture. We again saw that there are 6 stresses and 6 strains in the three-dimensional system, or the complete 3D stress state and 3D strain state. There are 21 independent elastic compliances for the anisotropic materials. These were the independent constants which are present in the A matrix relating strain and stress. This was a 6 by 6 matrix, and because it is symmetric, we ended up with only 21 independent elastic constants. And also we saw that for orthotropic material there are only 9 independent elastic compliances present. Now we saw that fiber reinforced composites are orthotropic material, and what happens here is that the x1 direction is the fiber direction and the remaining two directions are the transverse direction. And here also for a composite material you typically have 9 material properties which you need to determine to do various calculations. And finally we saw that for the isotropic materials you only have 2 independent elastic compliances, and therefore if you know Young's modulus and Poisson ratio, you essentially know the stress strain relationship for the isotropic material. So these are enough for you to estimate stress if you have been given strain, or to estimate strain if you have been given stress. The third value, which is G, can be calculated if you know E and mu. So this was the lecture where you got introduced to the special cases which come out of the anisotropic compliance matrix, which were the orthotropic case and the isotropic case. And I think now we know enough about the materials which are used as far as aerospace is concerned. So most aircraft structures are made of aluminum. Some parts are made of composites in some of the newer aircraft, such as the Boeing 787 or the Airbus A350. Most of the aircraft has been made of composites, but in more traditional aircraft, such as the Boeing 747, you have a widespread use of aluminum. But do remember that there are certain parts of the aircraft where high strength is required, where steel is also used, and there may be some parts which are also using some amount of titanium. So depending on that, you can use the material properties which are required in those cases. Now, one of the things which is going to be very important is the concept of principal stress. And in the next lecture, I'm going to talk about principal stress, because that is going to directly lead to the failure criterias for the aerospace structures. So I'll end this video now, and I will see you in a video sometime soon. See you then.